A cosine WT plus the phase shift, or omega T.
Thank you.
And then,
We're missing something.
oh,
Oh,
you have to do like the chain rule?
the
Yeah.
derivative of the inside, which is
Oh.
what? Isn't it just T?
No, it's just.
We're taking the derivative with respect to time.
Add a constant for now.
No.
It's just omega.
Just omega.
Oh.
Phi is a constant, and so the derivative is 0, and we're taking the derivative with respect to time, so it's just omega.
That makes sense.
The second derivative is
Just negative a omega sine of omega t plus the weird thing phi.
phi.
And then, oh,
We're missing something.
what if
It's omega squared.
Omega squared.
All right. So let's plug into our equation here. So I have k, negative ka sine omega t plus phi equals negative m times the second derivative, which is, oh, oops, that's not negative there. Times negative a omega squared sine omega t plus phi. Now let's cancel out stuff that we can. What can we get rid of?
Negative.
Okay? What else can we get rid of?
We get rid of one of the sign, or the sign?
We can get rid of A as well.
Yeah.
Get rid of the sign? And I heard A as well?
Yeah.
All right, so A can go, the sign can go, and what I'm left with is K. My spring constant is equal to mass times omega squared. Or omega is the square root of K over M. So for our particular situation where I pull it down and let go, we could actually now calculate. We have a value for K. We can find omega
So it's the square root
of K divided by 0.02.
the square root of 2.215 divided by 0.02, 10.524. Wait, no.
10.52,
4.
okay. Units?
Oh, and radians? No? No?
Not if you're stopping there.
Oh, radians per second.
Yes. All right, now that I have omega, what's the frequency? So imagine that I have a circle here, or I have a wheel, and I've got a little, some knob sticking out like that, and a light shining down from above, so that there's a shadow being cast onto the ground. So as the wheel rotates around like this, the shadow basically is moving back and forth in simple harmonic motion. As it rotates around, and we get the shadow, the time it takes for the whole thing to go around is the period. So t, the period, time for one complete revolution.
Wait, what is that dot?
That's a knob that's sticking out, that
Oh,
casting the shadow.
okay.
So I would have something like seconds per revolution, or seconds per oscillation, seconds per whatever repetitive motion there is. If I flip that over, and I figured out the number of revolutions per unit time, revolutions per time, that is frequency. So the frequency is just the reciprocal of the period. But we have this angular frequency down here that we need to somehow deal with, and so the relationship is, as this thing is rotating around, angular frequency is basically, you need to deal with basically the angle that goes through, and so it's 2 pi over t, which is just 2 pi times the frequency. So if you're talking about the shadow, you're talking about the angular frequency, and it happens to be equal to the angular speed as this thing is rotating around. So the speed, the angular speed at which this rotates is equal to the angular frequency. So the difference between angular speed and angular frequency is just context. They have the same units, they look and smell the same. So, yes, yeah, that's what it is. All right, so my frequency, so if I know omega, I want to find frequency. My frequency is just omega divided by 2 pi.
Oh, I got you on that.
In other words, my frequency is 1 over 2 pi of the square root of
1.6749.
units.
Oh. Does that have something to do with radians? I'm really bad at this thing.
Well, omega is radians per second, and this is 2 pi radians.
Radians per second squared.
Just seconds?
Second squared? No.
Radians per second.
Whatever seconds.
Which is the same as 1.6749 s to the negative 1 for those for that method, or 1.6749 hertz.
Oh. Okay, well, alright, I remember that from chemistry.
Okay.
Oh, yeah.
So now I know the frequency, I should be able to figure out the period. Because the period is just the reciprocal of that. So what is the period of our situation here?
Okay, so 1 over 1.6749, 1, 2, 3, 1, 0.597 seconds.
All right. Everyone, so far so good? Any questions? So we're about to make a prediction. So with a 20 gram mass on it, we're saying that that's the period. Notice that the amplitude is not affected. If I pull it even farther, so I have a bigger amplitude, then it's just going to be moving faster initially, and it offsets, and amplitude should not make a difference, ideally. So the prediction is that if the period is 0.597 seconds, well, let's do it. I'm gonna pull it down, let go. We're gonna do 10 oscillations just so that reflexes are less important. Who has the ability to do timing? If you have the ability, it'd be nice to have more than one person. Because inevitably in a group, there's somebody who hits things at the wrong time. when timing are ready, I'm gonna do 3, 2, 1, then go. All right, so 3, 2, 1. Oh.
Oh, did we not go? Gosh darn it.
Alright.
All right, ready now?
Yeah.
Yeah.
3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
I got 11.21.
10.991.
10.68. 10.90.
11.00.
I missed several of them.
10.58.
11, exactly.
All right, any others I missed?
10.68.
10.67?
68.
6.8. That hurt for the second thing. It's critical. All right, so like, Jacob, you're about to come tell me the average.
Yeah, I'm working on it.
Well, I know it's gonna be bigger than 10.58. Less
That's
than
would be less than
11.21.
11.21.
A little bit, I'm amazed that, especially with 110, the number of people who will average numbers together, get something completely out of bounds that we'll never notice.
10.9157.
Seconds.
So, if that is for 10 oscillations, what is the period for 1 oscillation? I think somebody just mumbled it.
Divided by 10?
Yeah. So 1.0916. We are really far off here. Why?
Oh.
Because it slows down.
Not the biggest impact.
Did we take into account 2 pi?
Take into account the what?
2 pi?
Yes, that's not the issue. We had a couple assumptions in here. And just so you know, I expected it to be off.
Wow.
We're gonna correct for it, and it should come out pretty darn close. What did we ignore?
Air resistance or friction?
We did ignore those, but those are not the big impact.
The loss of energy?
Oh, the fact that it slows down, not, over 10 cycles, it's not, that's actually not a huge issue.
So which one do you think is more correct? First or second? Like,
They both are. But they're for two different things. What is this taking in? This takes in, this is obviously reality here, but this takes into account something that this ignored completely.
Well, I'm gonna take an absolute shot in the dark here,
I was gonna say the Louise.
but
What, the 20 grams? Oh, no, it's definitely took that into
I
account.
feel like, cause if you multiply that top one by 2, you get.
Yeah, you get around.
You
Yeah,
get-
that just coincidence in this case.
Oh,
Oh.
dang, alright, never
Oh.
mind, alright, I don't got any more ideas.
Yeah, that's what I was fixated on,
All right, so let's see, what do we know?
but there goes everything.
We had, spin this around again. Let's see if Ben gets sick from flipping it back and forth. All right, so we had, K we did by, 0.02 times 9.8 over the mounted stretch, which I think was 8.85, or, sorry, 0.0. And that was 2.215.
Yeah.
per meter. And that was just, we had the spring, we put a mass to it, and it stretched down. We found omega, because that's the square root of K over M. And we had the K, and so this was square root of 2.215 over 0.02. and we got 10.524 radians per second.
Is the 0.597 just half an oscillation?
No, that should be for the full oscillation.
Okay.
I'm assuming all our math is done correctly here,
Okay.
but we just ignored something.
Right.
Weight of the spring?
Well,
Yes.
No.
Sorry, I don't know what you were about to say. Did you want to?
no, I just thought there was an error with 0.02.
Oh,
What was it? What was the mass? I forgot what.
That was a 20 gram mass hanging here.
Oh.
But all of this, Hooke's law, this assumes ideal spring. This was not an ideal spring. We do have to take into account the mass of the spring.
Dang it.
But not all of it. It's not like I can find the mass of the whole thing, figure out what part that is, and do a fraction there. But we do need to somehow figure out what is the effective mass of the spring and take that into account. And so let's do it. So then we get T is equal to, we did frequency net, which was 1 over 2 pi, or omega over 2 pi, 1.6749. And every period is 0.597 seconds, all right. So the problem lies there. That one number.
Well, that's just the weight, isn't it? Like, that's just the mass of the weight pulling down on the spring. That's not the weight plus the spring.
Right, mass.
Yeah.
Stick with mass here. BJ?
What about the 0.2 or 0.02 at the top as well? Would that change?
No, but that's
That's just-
good as is.
Okay.
Because it stretched that much because of that.
Okay.
So what we're gonna do here is oscillate this thing without the mass attached to it and figure out what is the effective mass because of just the spring itself. So pull the stopwatches again. We can do 10 oscillations. Okay. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Wait, what?
Did you stop when I got to 10?
I did,
Yes.
yeah.
All right, then, for those of you who stopped when you got to 10, sorry, I'm
8.8.
in my Sesame Street days there counting. What do we got?
9.007.
9.007.
8.8 seconds.
I got 9.28.
897.
I got 9.25.
8.64.
8.64. So, all right, so our average.
.9912.
And that was for 10 oscillations. And so my period is basically going to reverse what we had done here. It's 0.89912. So seconds. What is my frequency?
It'll be 1.1219. Did I do that right?
1.19.
1.11219. Sorry, hertz.
That?
Yeah,
Okay.
sorry.
So what's my angular frequency? Would be just 2 pi times that.
Uh, 6.983.
Oh, sorry. What are the units for frequency?
Hertz.
Hertz, capital H, lowercase z.
How was frequency, what was the equation you used for my frequency? Because I got a different value.
Oh, you're gonna, frequency should be 1 over the period.
Yeah, that's what I did.
Yeah.
1 over 0.89.
So what did you do?
So why is, how does, no, I understand, but, sorry.
Okay. Units of annual frequency?
Radians per second.
All right, so that is equal to the square root of k over m. So we're basically trying to find m right here. We have our value of k. So omega is equal, so we have 6.9839 is equal to the square root of 2.215 divided by m. This is mass of the spring, or effective mass of spring.
I got 0.046
Units?
kilograms.
And something just popped up here, sorry. Battery is running low, so I don't know how much longer this thing is gonna go.
I said 0.046 kilograms.
0.046 kilograms?
Yeah.
Okay.
It's on the board.
And just be aware, I think I'm gonna lose power soon. All right, so now we take the effective mass. So now let's go back over to here where we have 0.02. So we have the mass that we added plus the effective mass there. So this number is gonna change to 0.066 kilograms, which then changes that, which then changes this.